The last thing we're going to go over today, 514, is arc length. Okay, arc length, you're basically adding up the infinitesimally small distances between them. So say you had an arc length right here. Imagine you had a distance formula and you're adding up infinitely tiny, infinitely many distances. So you have all these little tiny distances and you're adding them up. Essentially, that's what this equation does. Okay, now if you're like, whoa, where'd this equation come from? I have the complete breakdown right here. So it says the sum of the distances, sigma means sum of the distances is equal to, this is just the distance formula. But then I made n go to infinity. So if you have n go to infinity, now you're using the integral. And then all these delta x's and delta y's become dy and dx. And then I divided by dx squared, and you end up with this equation right here. Now, this equation is the most important thing. But the main thing is you take the derivative, you square it, you add 1, you take the square root of it, then you do the antiderivative. Okay, we're going to go over many examples for this. It'll be fun. The arc length, the idea behind calculating the arc length with a definite integral is you're just adding up all the little infinitesimally tiny distances along this. Okay, so you're summing up the distances. This means summing up the distances, and you're summing them up along this entire interval. That's what this is right here. It's change in y over change in x. If you remember the distance formula, it's delta x quantity squared plus delta y quantity squared, and you're doing the square root of all this. Okay, that's why they have this here in this picture. Again, you don't need to worry about that. Here, you're summing up the distance, summing up, and then this is again the distance formula right here. You know, this is what I just wrote up here. Now, if you do it infinitely many distances that are infinitely thin, then you do the integral here. Now, if you have a dx and a dy here, what you can do is divide each of these by dx squared. And when you do that, you're factoring out a dx squared. It shows up right here. But anyway, the moral of the story is you need this. Okay, they use S for arc length. I use L because some books use L, some books use S. It doesn't really matter. Just make sure you know what you're doing. You'll see the answer key. I usually use L. I don't know why. I think because the book uses L, but it doesn't matter. Okay, so here's our first example that we're going to look at. It says y equals sine x from 0 to 2 pi. By the way, you're always going to be given the intervals on this, so it's really similar to average value, where they give you the interval each time. I need to figure these out. Okay, so we're saying, what is the arc length? That's what the L is, from 0 to 2 pi. So let me go to my calculator real quick, just so we can kind of understand what we're looking for. So you have sine x, and your y1. Your window, change it to 0 to 2 pi. And then zoom 0 to zoom fit. Now imagine running along this. Okay, you're running along this. Whatever length or distance that you're running, that's what we're looking for. Okay? Now, if we were going to estimate this, what's a good estimation for this? If you just looked at this and go, oh, this distance is probably going to be what? We can definitely say for sure that it's greater than what? From here to here, it's 2 pi, straight line. You're obviously going longer than this, okay? If you were going from point A here to point B, you'd want to do a straight shot, okay? If you were driving, you would want to drive straight there, okay? You wouldn't want to go all the way around and all the way up here. So you know that your L should be greater than 2 pi. Okay, you don't really need to think of it that way, but I like to just in case, because when I get my answer, I want to make sure it's greater than 2 pi. Because if it's less than 2 pi, then I don't know how that's possible. Okay, so let's use the formula that we have right here. Okay, the main thing that you need to do, I would always find the derivative first. Okay, you can plug it in there but then you're writing all this like the integral from a to b and the square root a million times. It's better to just do the derivative first. Okay, so that's what we're going to do. The derivative of y, this means derivative of y, is cosine x. Okay. Then I also like to square it right away. So that way I'm just putting it in right away as cosine squared. Okay. So that's what I'm going to do now. I'm going to do, so the arc length is, going from 0 to 2 pi. And we're doing the square root of 1 plus cosine squared x. with respect to x. And I'm just using the formula for this up here. I did my derivative and squared it, so I'm putting it in there. Okay, you should notice, hopefully, that you can't actually do this antiderivative. It's impossible. Okay, you have a function inside of a function. You can't use u substitution, which is usually what you would use if there's a function inside a function. So the only other option is a calculator. So moral of the story, a calculator is needed for many of these. Okay. It's also good practice to see, oh, I can't use my calculator. I can't use any integration technique, so I have to use my calculator. Okay. So let's go to our calculator then for this. Calculadora. All right, cancel out of all this. Okay, math 9, going from 0 to pi. And we're doing the square root of 1 plus cosine x squared. Let's check just to make sure. With respect to x. It's counting up all the little bits. Sometimes it takes a while. And then you have 7.640. So I went around to 2 decimal places. All right. So we have L being equal to the integral from 0 to pi over 4. Okay. We're going to the square root of 1 plus the derivative. I didn't do the derivative of that. Let's do the derivative really quick. Okay, so the derivative of ln is going to be 1 over whatever's after it. So we have 1 over secant x times the derivative of secant x. The derivative of secant x is secant x tan x. It's one of those formulas you have to remember. Secant x cancels, so you just end up with tan squared x. That's nice. All right, that's actually equal to secant squared x, this 1 plus tan x squared. I'm going to act like nobody remembers that from the trig properties, so let's just do our calculator with this. So we're going to say calculator needed. Okay. Yeah, it's something like that, 0.881. L is equal to 0.881. 3 decimal places, por favor. And there we go.